Good morning, everybody. So, we have completed 5 lectures in open channel flow. That too, the part one of open channel flow, that is uniform flow. Once again, I remind you, in the first 2 lectures, we have discussed on what is open channel flow, what is the difference between pipe flow and open channel flow. That's what we discussed. Then, after discussing that, what are the various types of channels? Then, what are the various types of flows? This is what we have discussed. So, after discussing this introductory part of the whole open channel flow, then in the third lecture, we have taken up the velocity distribution. Once the velocity distribution is taken, then what I have done in the series, after the velocity distribution, what are the geometric proportions of the sections that we consider in open channel flow? What are the sections that we consider in open channel flow? Rectangular, trapezoidal, circular. These are the things. Once that is covered, then we have taken up what are the main how to calculate or compute the discharge in open channels. For the calculation of the discharge in open channels, the important formulae for velocity, whether it is Chezy's equation, Manning's equation, Basing's equation, or Coulter's equation. So that we have discussed. And while discussing that, the important geometric proportions of any section, rectangular, trapezoidal, or circular, our main important things are number one is the wetted area, wetted perimeter, hydraulic radius, fourth one is top width, fifth one is the hydraulic depth. These are the things. There I told you what do you mean by section factor, and at the same time, what do you understand by conveyance? These are the two things I convey. Once this part is done, then we try to solve basically some problems with the different geometric shapes, how to calculate the velocity, how to calculate the discharge. That is what I have done in the first 5 lectures. Today's lecture is mainly focused at today's lecture, tomorrow's, next, so coming 3 lectures, and then 1 or 2 lectures for problems. So coming 4, 5 lectures deals with the most important topic of this uniform flow, which we call it as most efficient channel section. What do you understand by most efficient channel section? The most efficient channel section will be automatically the most economical section. So, what is the most economical rectangular section? What is the most economical trapezoidal section? What is the most economical circular section? So naturally, we decide about the section first. Once you have decided what are the conditions if this rectangular channel has to be called as most economical sections, how the dimensions should be. What is the thing dimensions, how the dimensions should be, then you call it as most efficient. But remember that the most efficient or most economical, generally it is only one thing, that is, the channel has to carry maximum discharge. A channel which can carry maximum discharge for a given conditions. That conditions are given cross-sectional area. For example, given roughness coefficient, a given bed slope. So these three are fixed: cross sectional area, bed slope, roughness coefficient. Under these conditions, a channel which can carry maximum discharge is called as most efficient channel section. That we will discuss first, and then we derive the conditions for the most efficient channel section. If the section is rectangular, if the section is trapezoidal, if the section is circular. These we will do it, and we do problems. With this, let us go straight away into the lecture. Right. So topic is most economical or most efficient channel section, right? A channel section, just now I told to you, a channel section is considered most economical, most economical when it can pass. Please see, when it can pass maximum discharge. This is the first condition you should remember. When it can pass maximum discharge for a given conditions I mentioned, for a given cross sectional area, right? Next, roughness coefficient. Roughness coefficient are nothing but CRN, and the bed slope. These three are fixed. These three are constants: area, roughness coefficient, and bed slope. Under these circumstances, a channel which can take maximum discharge, which can pass the maximum discharge, is called as most economical section. For example, we know continuity equation. We know continuity equation which says that Q is equal to discharge is equal to area into velocity, right? If A is constant, that's what we have mentioned. A is given. So discharge will be maximum. When discharge will be maximum? Discharge will be maximum. This is what we require if the velocity is maximum. So now for the maximum discharge, the first condition is the velocity is maximum. Then only it is possible. Now we know Chegis or Manning's equation C root Rs or V is equal to 1 by N R to the power of 2 by 3 S to the power of R. Chegis or Manning's. What they mentioned this these two are roughness coefficients. So they are given. Given means what? They are constant. Then this is also given slope, bed slope. So that is also, yes, is also given. So given value means constant value. So constant. So what is the remaining? V depends on what? V depends on only R. So V is maximum if R is maximum. This is second point. Then what is R? R is equal to A by P. This A is constant. When R will be maximum? R will be maximum if P is minimum, because A cannot change. P is minimum. So finally, what is the conclusion for maximum discharge? For maximum discharge, the first thing is velocity should be maximum. For maximum velocity, what should be maximum? R should be maximum. R is hydraulic radius. And if R should be maximum, then P should be minimum. So what I am going to use is, I will use this condition, right? We use this condition, that is P is minimum, to derive the conditions for most economical channel section. So where I started, actually, most economical channel section I defined as a channel which can carry maximum discharge. Under what circumstances? Given area of cross section, given roughness coefficient, and given bed slope. Right now, I have really how to really do it. So how to get the maximum discharge? The thought process is, what discharge depends on what? Discharge is equal to area into velocity. So area is constant. So discharge will be maximum when V is maximum. Then V equations are what? Chegis-Manning's equation. In that, if I see, all depends on only roughness coefficient R and S. N is constant, C is constant, S is constant. So what is remaining again? So V directly depends on R. So that means V will be maximum only if R is maximum. What is R? R is equal to A by P. A is constant. So when R will be maximum, A cannot increase. So when R will be maximum, when will be R will be maximum? Only if P is minimum. So that condition we are using it to derive basically the most economical section. So this is the starting point for me. So tomorrow, if somebody asks you to derive the conditions for most economical rectangular channel section, so most economical rectangular channel section, if I want to derive the conditions, derive the conditions. If that question comes, first I will explain the above thing. That means Q will be maximum. Q is maximum if P is minimum. This is the condition I am using it. Why I am using this condition, I already mentioned at the above. So now if I take it, for example, a rectangular channel section, I will take it. Suppose this is the rectangular channel section. Up to here we have the, so this is the depth of flow, right? And this base width is B as usual. So if this is, so what I will write, consider a rectangular channel section of bedwidth B of bedwidth B. That's what we have taken. And depth of flow. What is depth of flow? Y. Right? So what is area is equal to By. What is perimeter is equal to B plus 2y. So A is equal to By means what can I write here? B is equal to from this actually A by Y. So therefore, P is equal to if I substitute A by Y plus 2Y. You can ask why, sir, you are doing all this. Problem is basic. I told only three are constants. Area is constant. One is number one. Number two, I mentioned it as N. C or N is constant. Number three, slope. These three only should be there. So that is why B I want to write in terms of Y. So that's how I have written. So what is the now basically that is why I have done this problem. So according to basically the condition for maximum discharge, P should be minimum. For minimum or maximum of P, what is the condition for minimum of P? What is the condition? It is basically dP by dy is equal to 0 because A is constant. Already we have taken A is equal to given. That means it is constant. So assuming that it is important thing. Right, dp by d only variable in this is what y, dp by dy is equal to 0. So now let us find out what is dp by dy is equal to in the above thing. Dp by dy is equal to, if I do it for example here, minus a by, right, this is y square, right, and then because it is y to the power of minus 1, so if I take it on the other side minus 1, so that is why this minus has come, y to the power of minus 2, so that y to the power of minus 2 becomes actually into the denominator y square, but here plus 2. And what is the condition I mentioned? This should be equal to 0. Therefore basically if I write it here, if you see, minus a by y square is equal to 0, or a is equal to, for example, if I see what is a is equal to, minus a is equal to basically it's minus plus, sorry, minus a by y square plus 2 is equal to 0. So therefore if I want to do a by y square is equal to 2, right? A is equal to what? A is equal to by. Therefore, by divided by y square is equal to 2. Therefore, y cancel. That means what is the condition we get? B is equal to 2 by y. Or depth of flow is equal to y is equal to b by 2. This is the one of the conditions actually. So the what is this condition? How we can write? If depth of flow is equal to, if depth of flow is equal to half the bed width, half the bed width, a rectangular channel is, a rectangular channel is most economical. So this is first thing. One condition I have derived. Then I will take you another condition. R is equal to, you know, that A by P. A is equal to, we write by by b plus 2y. So just now we got one condition. This b is equal to how much we got? 2y into y. Just now that condition we derived by 2y plus 2y. So if you see it, 2y square divided by 4y. So 2 will cancel, 2 is there, y will cancel. Then what it will be there? Y by 2. So what is the second condition for most economical? So this condition is 2. So final conclusion is conditions for most economical, efficient, both are same. Rectangular channel section are number one, y is equal to b by 2. Number two, r is equal to y by 2. This you should really know that. Then only we will be able to really go ahead with this. So this is the simplest I have taken up. For your sake, I will take just a problem also so that we will go into the next problem. One example I will show you. A rectangular channel carries water at the rate of 400 liters per second. When bed slope is 1 in 2000. Find the most economical dimensions of the channel. If C is equal to C means Chaji's coefficient C. So this is what we have given. So he has given a rectangular channel section carries what the rate of this and the bed slope is this. Find the most economical dimensions. This is what he wants. So what we will do, let us take Q is equal to 400 liters per second. You already know because our unit is 1000 liters is equal to 1 meter cube. So volume, the discharge unit is meter cube per second. So immediately convert that into that. If you convert it, it will be zero point 0.4 meter cube per second. This is the first one. Then bed slope S is equal to S naught or S whatever you call it as long as you are talking about uniform flow, bed slope S naught, the water surface slope and the energy line slope all are same. So that's why most of the people in the textbooks they write S. Otherwise bed slope means we should write S naught. But as long as uniform flow you are discussing, no problem because all are same. So that's why generally they just use yes. That is the first thing. Then C is equal to 50. That is third. Then actually what are our conditions? The conditions are, what are the conditions? You tell me. The first condition is y is equal to, for example, rectangular channel. If you take it, write that figure also. So put this is y, this is b. Otherwise, y is equal to b by 2, first condition. Second condition is R is equal to Y by 2. These conditions you write. First write that. Then now we will take it. So what is the area of flow? Area of flow is equal to By, right? If I take what is B is equal to 2Y into Y. So it is 2Y square. That is what first thing. Now what is the equation I will use? Q is equal to A into V. This is A into velocity is what? C root or S. This is the equation, right? Then in this A is just now we got 2Y square, right? Then into C, right? Into square root of what is the most economical condition? R is equal to what? Y by 2 into S. This is S or S not, whatever it is. So now if I take it, what is the, what he has given basically. So if I take it, discharge is equal to zero point 0.4 is equal to 2y square into this is 50 into root of y by 2 into s is 1 by 2000. If this is the total thing, so if I do it actually the total thing, so what I am going to get is this. I am going to get it as, because all is in y only, 1.581 y to the power of 5 by 2. So therefore y is equal to, right, y is equal to 0.577 meters. So your job, major job is this only, how to calculate from this the y value. Calculator, use it and then immediately solve it like me. Then b is equal to 2y, right? Because already rectangular channel section conditions, once again here I am writing y is equal to b by 2. Second thing, r is equal to y by 2. These are the two conditions for rectangular channel. So I am using, so y is equal to b by b is equal to 2y. So 2 into 0.577. So naturally it is equal to 1.154 meters. So this is the first problem. I will take you another problem also before concluding this session. Problem 2. A lined rectangular channel with Manning's N. Previous one I have done it with the Chegis. Now this I am doing it with man. Is equal to 0.015, is 5 meters wide and has a flow depth of 2 meters with bed slope of 1 in 1600, retaining the rectangular shape of the channel and the total area of lining and the same total area of lining, that is mean, to what maximum discharge, to what extent can the discharge be increased, to what extent can the discharge be increased without changing the slope. First understand the problem, then we will do. What is the existing channel? The existing channel is Manning's coefficient this much, 5 meter wide, depth of flow is 2 meters. This is the existing channel. If I write, first thing is existing what? There are two things, existing, then how to increase. So if I take a rectangular channel, this is the existing one, right? So what he has given, B is equal to 5 meters. And what he has given, what depth is equal to? This Y is equal to, he has given it as 2 meters. These two he has given. Then what more he has given to me? S is equal to 1 by 1600 he has given. N is equal to 0.015 he has given. These two he has given. So then first discharge, I don't know. So what I need to do, first you find the discharge for the existing channel. So up to this, the problem is over. Then next is retaining the rectangular shape of the channel section and the same total area of lining. To what extent can the discharge be increased without changing the slope? That is what he is asking. So that we will find out. So and again remember that the area of lining should be same. So that is fixed. Keeping that, and then we will go. First let us find how, first how much is the discharge we know, then how much we can increase the discharge we can calculate. So what is the existing discharge, we will do it. What is our formula for the existing discharge? Q is equal to A into V. It is nothing but A into, because N is given, so that formula you write it, R to the power of 2 by 3, S to the power of half. So what is area? Area is generally By. By is what? 5 into 2. So 10 meters square. Then what is R is P is equal to B plus 2Y. B plus 2, 5 plus 2 plus 2. 5 plus 2 plus 2. So this is equal to 9 meters. Then what is R? It is 10 by 9. So this is R is equal to, right? Now knowing this, basically this, let us substitute in that equation. Discharge is equal to, area is 10, that is number 1. Then 1 by N is equal 0.015 into R is equal to 10 by 9 whole to the power of 2 by 3 into S is how much he has given, 1 by N is equal to 1600 whole to the power of half. So if you calculate it, Q is equal to 17.88 meter cube per second. So this is our first answer. So this is over. Then naturally the proposed. Proposed is what? That new channel, basically maximum for proposed is for maximum discharge. For maximum discharge, I use the conditions. What are the conditions? Number 1, Y is equal to B by 2. Number 2 is equal to R is equal to Y by 2. I will write this a bit. And what is the area of lining? Area of lining Suppose you take this is the channel, right? And channel is extending it perpendicular to the board, perpendicular to the plate. So if I take it, this perimeter, whatever this perimeter is there, this perimeter into perimeter into length, then that will give you the area of the thing. So now what is our already if I take considering unit length, because length is not given, considering unit length as length is not given. So area of lining is equal to, for example, now what is the already wetted perimeter? It wetted perimeter is a unit length. Then area of lining is equal to wetted perimeter. Already we got it is 9 above into length is 1. I told 9 meters square. Right? This is over. Then now what I should do it, now I am trying to find out what is the condition, b must be equal to b plus 2y, right? So what is the condition for most economical channel section? If I take it, b plus this is 2 into y is how much actually, b by 2, right? If I put it, what will be the things actually? If I say this is 2, 2 will cancel, b plus b, this is 2b. And 2b is equal to how much? 9. So therefore, b is equal to how much? 4.5 meters. So this is next. Then what is if b is equal to 4.5? Then conditions, one is conditions is what? Y is equal to b by 2. Second condition is r is equal to y by 2. When b is equal to 4.5, what is, sorry, what is y is equal to b by 2, 4.5 by 2. So it will be 2.25 meters. Right? But I kept actually the perimeter is area of lining as same basically. Kindly remember that. So it is meters. So two dimension. So based on these dimensions, now again calculate the new discharge. Previous dimensions are what? 5 meters, 2 meters. Now what the dimensions we got? 4.5 meters. The first one, if you remember, what is the first one? This is 5 and this is 2. This is the old one existing. What is the new one that we are getting basically? So this is basically if I take it. So this is 4.5 meters. This is 2.5. So that is the difference actually. So now based on this new discharge, new values, again discharge Q is equal to AV. It is equal to A into 1 by N R to the power of 2 by 3 S to the power of half. So A is equal to BY. BY is 4.5 into 2.25. It is equal to 10.125 meter square. Then actually P is equal to same, it should not change, right? Then basically afterwards, even if you calculate also, you will get the same thing. Please try to calculate. It is b plus 2y, 2 into 2.25. Answer is same, 9 only. So that's why p kept constant. Then r is equal to a by p. A by p means 10.125 divided by 9. So if I calculate it, it will be 1.125 meters. Right now, I will take it actually. I call it as Q1. The new one is Q1. So Q1 new one is equal to, now what is area is how much actually? 10.125 area into 1 by N is what? 0.015 into R is equal to how much? 1.125 whole to the power of 2 by 3. into 1 by 1600 whole to the power of half. If you calculate this, you are bound to get it as 18.125 meter cube per second. So original discharge, already you know the original discharge which we have calculated is 17.1. The old discharge is equal to old discharge is equal to 17.88 meter cube per second. Now the new discharge new discharge is equal to 18.125 meter cube per second. Therefore, increase in discharge is equal to 18.125 minus 17.88. If you see it, it will be 0.37 meter cube per second. So remember that it is not small amount. If you convert in liters and see 370 liters per second, per second. That is what I want to tell. So this completes as for us the rectangular most economical rectangular channel section. So kindly first can derive the conditions for the most economical rectangular channel section, and again after deriving the conditions for most economical rectangular channel section, you take up 2 3 problems so that you will be more confident in taking up the things. So this is what I wish to tell you at this stage. And now I will basically with this we will stop the lecture here and take up trapezoidal channel in our next lecture. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.